So here are some questions that we're going to work out on electric currents, drift velocity, change in resistance with temperature, which includes Ohm's law, the definitions of resistivity, electric power, and its calculation. So the first problem is a simple one that talks about a bird standing on a DC electric transmission line carrying 3100 ampere. The line has 2.5 times 10 to the negative 5 ohm resistance per meter, and the bird's feet are 4 centimeter apart. What is the potential difference between the bird's feet? So here the line has 2.5 times 10 to the negative 5 ohm resistance per meter. So for each meter. And the bird's feet are 4 centimeters apart. So first we got to change the 4 centimeters into meter and calculate the resistance of that part by multiplying the resistance per meter with 0.04. And after we get the resistance of that part, we get the voltage or the potential difference by calculating the current, by multiplying the current with the resistance. So here it is, resistance per meter multiplied by 4 times 10 to the negative 2 meter, which is 4 centimeter, gives us the resistance. And then once we get the resistance, you calculate the voltage by taking the product of the current with that resistance. The current is high, it's 3100 ampere, so multiply it with the resistance and you get the voltage. That's a simple question to begin with. So here is the second question. It says a 12-volt battery causes a current of 0.6 ampere through a resistor. What is its resistance? And how many joules of energy does the battery lose in a minute? You have the voltage and you have the current. Calculation of resistance is a simple application of Ohm's law. Resistance is voltage by current, that gives 12 by 0.6 ampere, which gives the resistance as 20 ohms. Now in the B part, how many joules of energy does the battery lose in 1 minute? So we can find the power in the electrical circuit by taking the product of voltage and current. And power is the energy produced in 1 second. So once we get the power, all we got to do is multiply it with 60 seconds, which is 1 minute, to get the energy in 1 minute. So here it is. Potential energy is VI delta T. I did all of that in one step. And we would get the energy lost by the battery in a minute as 432 joules. In this question, a length of aluminum wire is connected to a precision 10-volt power supply, and a current of 0.4212 ampere is precisely measured at 20 degrees Celsius. So you're given the voltage and you're given the current. The wire is placed in a new environment of unknown temperature where the measured current is 0.3818 ampere. What is the unknown temperature? So now you have a new situation and the current is different, although the voltage is the same. That means the resistance has changed because the temperature has changed. In fact, the current has dropped. That means the resistance is increased. For conductors, the resistance increases with temperature. So we can find the original resistance and the new resistance and use the formula for variation of resistance with temperature in order to calculate the unknown temperature. So the original resistance is the voltage by current, which gives 10 divided by 0.4212. That gives us the original resistance as 23.74 ohm. And now the new resistance, remember that the voltage is the same, and so divide that by the new current. And when we do that, we get 26.19 ohms. Of course, the resistance is increased. And then this is the formula for variation of resistance with temperature. And remember that alpha there is a constant called the temperature coefficient of resistance. R is the new resistance, R naught is the original resistance, T and T naught are the temperatures. So now mathematically we need to separate the T, which is what we are looking for. T naught is given as 20 degrees Celsius. So it's just now algebra where you separate T from all the other factors. I'm doing it step by step. And first I've got R by R naught minus 1 on the left side. Now I have T minus T naught, and then the last step, T is going to be, well, I'm going to calculate that, and then, I put it backwards. So it's now 26.19 by 23.74 minus 1 divided by alpha. Of course, the value of alpha will be given. So that's the alpha for aluminum that will be given. So when you do that, you get T minus T naught as 24. Actually, you get 24.1. And so T is 24.1 plus 20, that is 44.1 degree Celsius. Now, in this question, we are trying to situate or trying to create a combination of a conductor with a semiconductor so that their resistance remains unchanged at all temperatures. Oftentimes, we need a resistor that remains constant even when the temperature changes. Now, for that, we can combine a conductor and a semiconductor. The reason being that for a conductor, as the temperature increases, the resistance goes up. But for a semiconductor, as the temperature increases, the resistance goes down. So if we have optimum values, we can keep the total resistance the same. So that's what this problem is talking about. If a 3.70 kilo ohm resistor is made from a carbon resistor, which is a semiconductor, and a nichrome wire, which is a conductor, so that the total resistance is independent of temperature, what are their individual resistances? Okay, so the only thing that's given is the total resistance, and of course, the temperature coefficient of resistance of both will be given. So alpha for nichrome is given. Now, alpha for carbon is negative 0.005 per Celsius. That's also given. And this is the formula for variation of resistance with temperature. And I'm just separating R minus R naught is equal to R naught alpha T minus T naught. And the reason is, excuse me, because I know that R minus R naught, which is the change in resistance, R minus R naught, the change in resistance for nichrome and carbon should be equal and opposite. So whatever one increases by, the other one should decrease by. That means the net change becomes zero. So that's why I have separated the change in resistance. So now I have the change in resistance for nichrome equal to the change in resistance for carbon. And then the formula for change in resistance is right here. So what I've done is I've used that. Delta T gets canceled from both sides. And then I rearrange to get the ratio and set it equal to alpha C by alpha N. which we have. So when I do the math, I get 1.25, which means the original resistance of nichrome is 1.25 times the original resistance of carbon. And we have that. And now we can use what we already know, that their total resistance must be 3.7 kilo ohms, which is 3,700 ohms. So the sum of the resistance must be 3,700. And then I substitute the resistance of nichrome as 1.25 times the resistance of carbon, which will, now 1.25 plus 1 is 2.25. That gives the value for the original resistance of carbon as 3,700 by 2.25, which is 1,644 ohms. Now, once we know the original resistance of carbon, we can take the difference and find that of nichrome. So that's how we work out this problem. In this question, number 5, the current in an electromagnet connected to a 240 volt line is 17.5 ampere. So you have the voltage and you have the current. And obviously the current is high. And at what rate must cooling water pass over the coils if the water temperature is to rise by no more than 6.50 degrees Celsius? Well, we know that whenever a current flows through a conductor, heat is produced. And the heat produced depends on the square of the current. Since this current, 17.5 ampere, is big, there's going to be a lot of heat produced. And now we need to pass cold water over it. And the question is, what should be the volume of water passing per second to maintain the temperature at an increase of 6.50 degrees Celsius? Because if we don't have the cooling system, the temperature is going to keep rising. We don't want that to happen. Okay? So first we need to find out the heat produced in this case. And second, we need to use an idea or the formula for heat absorbed by the cold water. And the heat produced in a conductor, as I mentioned, is I squared RT. I squared times resistance times time. So, but I've used I times current times voltage here, which is the same thing. I've used current times voltage. So I got 4,200 watts as the heat produced. That's the heat produced per second, because 1 watt is 1 joule per second. And then the heat absorbed by water is mc delta T, where C is the specific heat capacity of water. Water has a high specific heat capacity, actually 4,186 joules per kilogram Celsius, and then the change in temperature is 6.50. So when we do the math, we get the mass of water that has to be passed per second. When we do that, when we rearrange, you can see the units working out. The unit is kilogram per second. As you can see, the kilogram flips to the top. So you get 0.154 kilogram per second, which is 0.154 liter per second, because 1 kilogram of water is the mass of 1 liter of water. Okay? So 1 liter of water always has a mass of 1 kilogram. Therefore, we should have a rate of flow of 0.154 liters flowing through every second so that the heat is continuously being removed. This question has to do with drift velocity. So, you know that electrons, while they move through a conductor, continuously collide with the atoms in the conductor. the atoms are closely packed, that means there will be numerous collisions per second. So the electrons are compelled to move because of the potential difference produced by the battery. But as they move, they continuously collide with the atoms and lose energy. So, two things: the electrons are actually moving really slowly. That's why their velocity is called the drift velocity. Number two, this is the reason why a current flowing through a conductor always produces heat. It's the lost energy that is given out as heat. So here we have a 0.65 millimeter diameter copper wire. That's a real thin copper wire carrying a tiny, tiny current of 2.3 microampere. Micro is 10 to the negative 6. So that's a real small current. And we are asked to estimate the electron drift velocity, the current density, and the electric field. So first of all, the formula for drift velocity comes in this way, where J is the current density. It's a vector. Remember, J is current density. N is the number of free electrons in 1 meter cube. Number of electrons, free electrons in 1 meter cube. E is the charge of the electron. And V sub D is the drift velocity. So when we make the drift velocity the subject, and then remember that current density J is actually I by A. Current density is the current flowing through 1 meter squared. So first I put J, but then next I'm going to replace J by I by A. So I get I by A N E. So let's focus on the little n. What's n? Little n is the number of free electrons in 1 meter cube. So since this is copper, we will be given the atomic number of copper. And so which shows how many atoms are there in 1 mole. And so we know the number of atoms in 1 mole. We know the Avogadro number. And using these two, we should be able to figure out the number of free electrons in 1 meter cube, like I'm going to show you. So caps N, I'm going to show it on the left side. Caps N is the number of atoms in 1 mole, and M is the mass of 1 mole. So now, see what I've done is, I've shown that, little n is actually caps N by volume, because it's the number of free electrons in 1 meter cube. That's what we have here, because the masses will cancel out. But remember that mass by volume is density. So that's what I'm going to represent the little n as. So the little n here is represented by N by M density. And then you have the E, and then you have the A. A is the area of cross section, which is pi r squared, because it's circular. So pi times, instead of radius, I have d by 2 whole squared, diameter by 2 whole squared. And now, so that 2 squared becomes 4. You see this 2 squared becomes 4 and goes to the top. As you can see that goes to the top there. And then you have I, this M is here, it's come up, and then you have N rho E pi d squared. Okay, so that's what we have. So we have the current as 2.3 times 10 to the negative 6. And mass is the atomic mass is 63.5 times 10 to the negative 3 kilogram, because we need the mass in kilogram. 63.5 is the atomic number, or the atomic mass, it's the atomic mass. And then we have the Avogadro number, which is caps N, which is 6.02 times 10 to the 23. The density of copper, which is 8.9 times 10 to the 3. The charge of the electron, 1.6 times 10 to the negative 19. And then pi times the diameter, which is given as 0.65 millimeter, in meter it would be times 10 to the negative 3 whole squared. And when we do all those calculations, we get the drift velocity as 5.1 times 10 to the negative 10 meter per second. Look at how small that velocity is. That's why it's called the drift velocity. And I hope you understood this. It's quite a lot of substitutions, but it's understandable. And now the B part. You're asked to find the current density. That's easy because current density is just the current divided by the area of cross section. So the current is, and the area of cross section is pi r squared. So the current is, once again, I put it in terms of the diameter. That's why you have that 4, because the radius is d by 2, and when you square it, the 4 goes to the top. I hope you understand that. So current is 2.3 times 10 to the negative 6 by pi d squared, and you get 6.9 ampere per meter squared. Notice the unit, ampere per meter squared. And then we can find the electric field in the cable. Electric field is just voltage divided by distance. Correct? But electric field can also be given by this formula. It can be related to the current density by using this formula. J is 1 by rho times E. So E is rho J. So you get 1.6 times 10. We got to be really, really careful here. This rho is not density. This rho is resistivity. So that is resistivity. So the resistivity of copper is given, and then you multiply that with the current density to get the electric field, okay? So we got the current density as 6.9, you multiply and you get 1.2 times 10 to the negative 7 volt per meter. So once again, remember that the rho here is density, but the rho here is resistivity. I picked this question just to show you how big the temperature of the tungsten filament is. Even in a flashlight bulb, it gets so hot. In fact, most of the energy is wasted in the form of heat. Only a little is transformed into light. So a tungsten filament used in a flashlight bulb operates at 0.20 ampere and 3.2 volt. If its resistance at 20 degrees Celsius is 1.5 ohm, what is the temperature of the filament when the flashlight is on? So this is clearly the variation of resistance with temperature. We've done that before. So here is the formula. Resistance at any temperature is V by I, first of all, by Ohm's law, so we can get that resistance. That is the resistance at 20 degrees Celsius. And then here is the formula for the change in resistance with temperature. Alpha is given, again, alpha of tungsten is given. So like before, I'm rearranging it to make T the subject. So this is a repeat problem. And so you just have to do the algebra, separate the T, and finally I get T is T naught plus 1 by alpha, R by R naught minus 1. Then I substitute the values and get the temperature. Like I said, I picked this question just to show you that the temperature is really high. Let's see what we're going to get. So alpha for tungsten is given, and you get, oh my goodness, 2,168 degrees Celsius. That's the temperature, even in a flashlight bulb. Remember, the light bulbs that are used on AC in our homes, they go to much higher temperatures, like 3,500 degrees Celsius. So that's why we need to switch to LED lights, light emitting diodes, or even the old conventional fluorescent lamps are much better. That brings us to the last question. A copper wire of diameter 0.259 centimeter is used to connect a set of appliances at 120 volt, which together draw 1750 watts of power. Okay? So what power is wasted in 25 meter of this wire? What is your answer if the wire of diameter 0.412 centimeter is used? Something that we don't realize in real life is that if you use a long extension cable to connect something, we are wasting power. Because heat is produced in that extension cable, and the longer the length of the extension cable, the more the heat produced. So in this case, we have 25 meters of the cable connecting. It's not an extension cable here. But nevertheless, there's going to be a lot of heat produced. So let's find out the power wasted. So the current is the power divided by voltage from the power formula, and we get the current as 14.6 ampere. And then the power produced is I squared R. And so the resistance needs to be calculated, and we know that the resistance is given by rho L by A. Here the rho is resistivity. Resistance of a conductor depends on the resistivity, which is dependent on the material, depends on the length, and inversely on the area of cross section. So I've substituted the value of R as rho L by A. So using that, we can find the power dissipated. So the resistivity is 1.68 times 10 to the negative 8. And then you have the length as 25, and the area is pi r squared. So I've taken half of this and then changed it into meters here. And I get 16.95 watts wasted. So in the B part, what is your answer if the wire of diameter 0.412 centimeters used? So you see that it's a thicker cable now. When it's a thicker cable, the resistance decreases. When the resistance decreases, the power wasted also decreases. So let's find that. So once again, we do the same thing. The current through it stays the same, and the resistance is recalculated with the new radius. The length is the same, so the new radius is coming up. Half of this changed into meter, and you get the power wasted as 6.70 watts. So here I picked 8 very important questions that dealt with resistivity, that had the variation of resistance with temperature. We used Ohm's law. We took a clear look at the microscopic feature of the flow of current, namely how the electrons move really slowly. I'm talking about the drift velocity. And then we also considered the power in electrical circuits. This is fundamentally a very important chapter before we get into DC circuits, where we start combining resistances and we study about Kirchhoff's laws. So this chapter is really important, not just for the exam, but also for a clear understanding of the chapters to come. So I hope all of you will spend some time and prepare for the exams ahead by looking at this video and understanding it clearly. Thank you. We'll see you on the next video.